First thing I'm going to do is finish off a couple of examples from the section that we didn't quite get finished last time. Oops, there we go. I'm closing windows that I shouldn't be. So let's try and move this thing up here out of the way. Okay. So we've got two questions I want to cover. They're quite, one's pretty obvious, this one, and the other one's pretty sneaky, and will take a little bit of time. And then after that, we'll move on to our next section. Before they do that, to remind you that a week today is going to be your midterm, and that in the midterm, in our case, you've got a 2-hour window to do it. 10 till 12 is the 2-hour window, and the other one will be 11 till 1. So if you can't fit it in those 2 windows, or you need different arrangements, tell me about it and we'll think something out. In your case, what's going to happen is that the test is going to be in Canvas. It will be a PDF, and that you'll be doing all your working, and you'll be using the program Microsoft Lens or some other program if you've got some you know how to use, and you'll upload it into Canvas. So if you've had me before, you know the routine. So that's what the midterm's going to look like. It's worth a lot of points. You want to be ready for it. You want to get as much preparation as you can, and good luck when it happens. Yes, Rosie.
Is there going to be a practice midterm available on Canvas like you do for the finals and prior classes?
There should be one. I just aren't sure where it is. If I can find it, I'll put it on. If I can't, I guess my advice will be look at your homework, because that's kind of where I'm going to get my questions from.
You mean like exact homework questions?
Well, never exact. Similar. I might change something a 36 to a 49, but the gist of it will be the same. Yeah. You won't get questions that involve graphing in the sense that show me which one of these 4 pictures is the surface. I mean, you can do that in Desmos, but I don't need to see it. So, although Desmos is helpful for a lot of situations, so you probably end up using Desmos anyway, but only for your own benefit. Well, when you do your midterm, try and remember that all the working is important. So try not to cut corners, because if you make a mistake, I can give you partial credit, but I kind of have to see it. Right, let's get started on this one. There are 2 questions. This is the first one of them. We're being asked to find the surface area of this surface, z equals xy, and it's a part of the surface that lies within this cylinder. So this guy here is basically D, and since it's a circle and the radius is 6, it kind of makes sense that, that's for the next question, kind of makes sense that you do it in polar. In this case, it's a full circle, so you do 0 to 6, 0 to 2 pi, right? And the function z equals xy. So when we do the surface area, it's going to be the double integral of the region D, which is basically that guy, of the square root of the partial derivative of this function with respect to x squared, and the partial derivative of this function with respect to y squared, plus 1 dA, right? So that's pretty much a standard integral that you use for surface areas. And hopefully when you, let me move this a little bit, there we go. Hopefully when you do this, you'll have it written down somewhere when you do your midterm. So in our case, it's going to go from theta equals 0 to 2 pi, from r equals 0 to 6. If you take the derivative of this function with respect to x, you get y and you square it. If you take this function with respect to y, you get that guy and you square it, plus a 1. And the dA becomes r dr d theta. So far, so good. Now, what you have to, obviously, you have to do here is you have to convert this thing into polar form. but it's actually not that hard to do. Would you agree this bit here is r squared? So it's r squared plus 1, and I'll stick the other r at the side here. And this is kind of where I'm going to finish this question. Or maybe one more line. I can separate out the thetas, which is this guy, and the r variable, just this guy. Now, if you can do it as we can here, doesn't it just become a Calc 2 question? Okay, what technique will you use to integrate this ugly expression?
That would be a U sub.
Correct, and the U sub will be?
The U will be r squared plus 1.
And off you go and do what you need to do. So are you okay with me just dot, dot, dot in that, right? You can finish it in your own time. And that's a pretty standard one, but I don't believe I got to that one. And so I did it. And now this ugly thing. We haven't quite done one like this, and this is kind of the representation of questions where you have a surface, but it's not the typical on the ground up to where it meets the surface. And this one is, you've got a sphere, and you're cutting it at basically a height of 6. Z equals 6 is just parallel to the floor, right? But it's a height of 6. And we're being asked for that little bit. Can you imagine you've got an orange and you cut off the top and you made this little bump? We're trying to find the surface area of that little bump, right? Now, it's not a sphere. It's a piece of a sphere, right? And so we have to incorporate that. Now, the region D is hidden. It's not that clear who the region D is. So let me write down what we know. We have a surface of a sphere, which is that. And we have a line, a plane, I should say, Z equals 6. Now, when this sphere interacts with that plane, doesn't it basically cut it? And what you get is a little baby circle. You can see what the boundary here is, the baby circle I'm talking about. And that's the D that we need to find. The interaction of the big surface with the Z equals 6. Any suggestions how we could come up with the equation of that baby circle, which is what this guy would be if you shrank it to the floor?
Well, we could find the diameter of the circle created at that height.
Mm-hmm.
We could plug in our Z value in our equation and then use that to find the 0. Or use that to find out where it would be if it was, that point was at 0.
Okay, let me see if I got you. So you know that, and I'm going to put that into here. And that gets me x squared plus y squared, add 36. And that gets me x squared plus y squared equals 28. So that circle, that thing there, if you projected it onto the floor, wouldn't you get a circle of radius the square root of 28? And that's what we needed.
It's kind of like the cylinder in a box question that we had earlier on surface area.
Yeah, I mean, it is now a cylinder, isn't it? You know, it's a cylinder going up. So although you didn't tell me what the area or what the surface on the floor was directly, don't I now know that that floor would be just the shadow of this one? And so it's that. So I now know D. It's a complete circle. So it's 0 to 2 pi. It has a radius, right, of 28, which means R goes from 0 to square root of 28. Are you comfortable about how I found this circle on the floor based on a sphere meeting up with a Z equals 6 plane? So our double integral for the surface area, which I'm now going to move over here, is going to be from theta equals 0 to theta equals 2 pi, and from r equals 0 to r equals the square root of 28. Now we've got a guy in here that we haven't quite figured out who he is, and then it's going to be r dr d theta. And the guy that's in here shouldn't that be the surface of the sphere? Except the equation is written in a rather ugly way. It's written like that. So I need to take this information and convert it basically into Z, right? Z is f of xy, right? Any suggestions how this could become eventually the guy that goes here?
It's
Gonna
gonna
be
be
square
horrible,
root.
but it'd be 64 minus x squared minus y squared.
And then Tim said take a square root.
Yep.
Yeah, and it'll just become 64 minus r squared.
Yep.
Well, it'll be 64 minus r squared times 1.
Well, you don't need the one. You can have that.
If I don't
Right.
write the 1, I don't know where the sine and cosine went.
Oh, okay. Well,
Don't forget the plus 1, so it'd be 65.
no, it's just 64 take away after square. I think what he, if I'm putting words
What I'm talking
in,
about is there's a
It's this
trig
guy.
identity where, yeah, you factor out the sine, you factor out the r squared, and then sine squared plus cosine squared equals 1.
so that's what
That's the way
Tim's saying.
yeah.
It's helpful for him to put the times 1 in. Other people would just write r squared, right? That's what he said. So what we have here is 64 take away an r squared times 1, or just 64 take away r squared. Do you recognize this guy here? By that I mean, well, maybe one more line will help. I can separate this fella out. I can do it as a theta and this guy. Yes.
Wouldn't we need to do the partial derivatives for the formula?
Oh God, I'm looking at the wrong one. Ay, 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 ay. Oh dear, if I was, my brain is thinking of triple integrals, which we haven't done yet. So let me set this fella up again, and you are quite right. And the one that you're talking about goes like this. It's the square root of this guy. Oh, yeah, yeah. No wonder I kept that one separate.
Well, it's going to be a u sub.
It's going to, yeah, eventually, but before we get there, we have to tackle this problem. Don't we have to find the partial derivative of this guy with respect to x and then square it? And the partial derivative of this guy with respect to y, square it, and then add a 1. So this fella will need to be written as that guy to a half. So when you do his derivative, you're going to get 1/2 64 take away x squared, take away y squared, reduce the power by 1, and then won't you have to differentiate with respect to x? Now that
Would
and
give us
that,
a -2.
that's a negative. Are we good? Yeah. Okay, that's a negative. That's going to be an x. And we've got 64 take away x squared, take away y squared to -1/2. And then if you square this guy, you're going to get an x squared, a 64 take away an x squared, take away a y squared to -1. I guess I could write that as a fraction, but are we comfortable with what that guy looks like? Now, if I do this fella, can't I just use symmetry? Right, let's put all these pieces in here. If you differentiate this guy squared, this guy squared plus 1, you're going to get these two integrals. Then you're going to get the square root of that guy. So that's going to be x squared over 64 take away x squared, take away y squared, plus y squared over 64 take away x squared, take away y squared, plus 1. And then we're going to have an r dr d theta. There. That was a lot uglier than just a double integral. So far, so good? Still with me? Okay, got nods. This is not nice. I'm trying to figure out how I could make this prettier. And the answer I'm coming up with is not very good. So I'm wondering if there is a way around this. And essentially there is. I'm going to combine certain things together. I'm going to combine these two together. So I'll forget about all the double integrals in that. Let me just focus on making this guy as pretty as I can in terms of r and theta, in terms of polar. And then once I've figured out a nicer way to write this guy, then we'll return to this integral. Hopefully it's something good. I'm going to add these two together. So that gets me x squared plus y squared over 64, take away x squared, take away y squared plus 1. Are you comfortable with that? Since these share a common denominator, I can add them. Terence, question. Terence? Oh, it's gone. Right. Can't this guy be called r squared? And can't this be called 64 take away r squared plus 1? Do you agree it's getting a little bit prettier? What?
A lot prettier.
Okay. Now, I don't like ones and fractions, so how about calling this one 64 take away r squared over 64 take away r squared? Would you agree that's allowed? And that one as well. Now, if you add these two fractions together, you actually get 64 over 64 take away r squared. Great. Now, not much, but can I take the square root of the top and bottom separately?
Yep. Oh, yeah, this is like that one where it's like we had to find the partial cylinder with the square, and you had to like do the sine inverse.
Oh yeah, but this guy's still got an r left over. So we're going to be in a much better place than that one. Yeah, if it was just this ugly guy, you'd be dealing with some kind of inverse sine guy. But look what we have now. How am I going to
have a bit of a weird U sub type situation?
Yeah, and who's the u sub going to be?
The 64 minus r squared.
And off you go, and you are done. So, I mean, it was ugly, but I guess it came out okay in the end. You agree? A u sub. And you're going to have some way, a multiple of 1 over the square root of u, and you call it u to a half, and you'll get ridiculously ugly answer, but it will work. That's the end of surface areas. Is there any questions before I move on about what we just did? Okay. Next fella is triple integrals. I believe it's called 11.6, but let me double check. And it's 15.6.
Triple integrals sound intimidating.
They're not actually. Do you know where you've went from single integrals in calc to double integrals? Are you feeling comfortable about double integrals now? You know, right? Not yet. Well, hopefully you will. Triple integrals are essentially have this shape to them. You have a triple integral of some region R, a function of x, y, and z now, and then you have a dv. That would be a region R of some function f of x, y, z, and dv will be dx, dy, dz. So
Well,
aren't you basically just doing 3 integrations instead of 1?
Well, now that I see I just have to draw more squiggly lines, I'm cool with it.
Yeah. And a lot of what you've done in double integrals, you're going to continue to do in triple integrals. You're just going to do it 3 times instead of 2 times, right? So let's start with the simplest regions, right? What am I trying to think of names for them? Cuboid, I can unspell it there. There we go. Cuboid regions in 3D space. So let's look at triple integrals of cuboid regions in 3-dimensional space. An example, suppose R was the following region. X equals 0 to 1, Y equals 1 to 2, and Z equals 1 to -1. Now, if you try to draw that in 3D space, would you agree it ends up being a cuboid, which is a mathematical name for a box? And in that box in 3D space, there is some function acting on it. Maybe the function's a temperature function. In other words, if you tell me the X, Y, Z coordinate, I will tell you what the temperature is at that instant in 3D space. So do you see we're now moving into more realistic situations? Isn't the world typically 3D? I guess you could say it's 4D, but definitely 3D, right? And so you have to be able to integrate and deal with things in this 3D world. So can you imagine this box I'm talking about floating in space? And the temperature X, Y, Z is 50, 100, 200, 400. If I integrate a triple integral of that, what I'm basically finding is the total amount of heat, i.e. temperature, in that box. Can you imagine that some areas it's quite hot and others it ain't that hot at all? Right. So you can think of triple integrals as summing up something, but summing up something in 3D space. Right, so can you imagine that box was again floating in midair, right? For some reason we decided to float it in midair. Couldn't you be told the density of that function at any given point X, Y, Z? Then if you did the triple integral, do you know you've just found the mass of that 3D object? Right, so you're summing the density gets you the mass, right? If this 3D object had charges in it, aren't you, when you do a triple integral, aren't you adding up all the charges? I know that's called something, it's in coulombs. Is it just called total charge or something?
Well, coulombs is the unit that is used to measure the total charge. Yeah, I think we just probably call it total charge, or sometimes it's farads.
So you can imagine you would want to do for 3D objects, right? The entire 3D object, that thing. So let's suppose that in this region here, my function f of x, y, z is x squared plus y squared plus z squared, right? Could be anything, but in this case, I'm making it that. Now, what we're going to do then is we're going to find the triple integral. And it's going to go from x equals 0 to x equals 1, y equals 1 to y equals 2, and z equals -1 to z equals 1. You won't see the textbook put these guys in, but honestly, the number of mistakes I make, if you just put 0, 1, 1, 2, and -1, 1, isn't it dead easy to forget who's the x, the y, and the z? And so that's the only reason it's there. If you choose, I don't need that, I know which one's x, y, and z, then don't bother, right? But for me, it's helpful. In this case, it's an x squared plus a y squared plus a z squared. And the order is going to be, in this case, dx, dy, and dz. Does that make sense in the order that I've written down these, that they match this? Great. Now, I'm going to do this one all the way to the end. But do you notice that these are all numbers? If I wanted to, couldn't I integrate it z first, y second, and x last? As long as I move the limits of integration to match the variables order. Would you agree? Can I separate this into 3 distinct integrals? No. If it had been x squared times y squared times z squared, couldn't I then separate it into 3 integrals, right? So It's great if you can, because honestly, it saves you a whole load of work if you can do that. But don't expect it to happen too many times, right? It's more likely or not that if they're all numbers, at least you can switch the order. In this case, I don't think it makes a darn bit of difference. But can you imagine there might be some questions where doing the X's first, the Z second, and the Y's last might be less work, right? Just because this function here is really ugly in whatever one of those three variables I just said, right?
I think if you have the zeros first, that tends to help because then at least you're able to get rid of the zeros instead of having a plus and minus for making it ever expanding.
Right, and things grow. If they get bigger, you don't really want that. So Z equals -1 to Z equals 1, Y equals 1 to Y equals 2, and I'll just do this guy. And then I'll do a dy dz after that. Now, if you integrate this with respect to x, you get 1/3 x cubed, you get a y squared x, and you get a z squared x. And they are going to be evaluated at x equals 0 and x equals 1. Are we comfortable with that integration with respect to x? Right. And so I'm going to have z equals -1 to z equals 1, y equals 1 to y equals 2. This is dangerous, but I'm going to try it. Plug 1 in, you'll get a 1/3 plus a y squared plus a z squared. If you plug in 0, everybody disappears. Are we comfortable that that's what the integral is? Now, at this point, isn't it now a double integral that we should be pretty familiar with, aren't we? And so I just basically, keep turning the handle. So I'm going to do this fella next. So it's going to be the integral from z equals -1 to z equals +1. If you integrate this with respect to y, I get 1/3 y plus 1/3 y cubed plus y times z squared. And that's going to be evaluated at y equals 1 to y equals 2. And we get, well, that's 2/3, 8/3, and 2z squared. Take away 1/3, 1/3, and a z squared. Just double check. 2/3, 8/3, 2z squared looks good. 1/3, 1/3, and a z squared. So I get 2/3, 10/3, take away 1, 9/3, take away 1, 8/3. So it looks like 8/3. I have a 2z squared, take away a z squared. Looks like I've got 1z squared left over. You're all used to me by now. Does that look good? Right, so just keep going. 8/3 z plus 1/3 z cubed. Evaluate from z equals -1 to z equals 1. And that's going to be 8/3 plus a third. Take away -8/3, -1/3. And 8 and 1 get me 9/3. 8 and 1 get me 9/3. Would you believe it? I never expected such a nice answer. It's 6. Now, triple integrals, if they have no context to them, if it's just find this triple integral, you can get positive answers. Could you get 0? Could a triple integral be 0 if it's got no context, right? It's not a volume or an area or anything else. Could it be 0? Yeah. Could it be negative? Right. Isn't that the same as Calc 1? Couldn't a single integral, if there's no story attached to it, right? You're not finding the volume or the area or something, right? Triple integrals can take any value they like. So don't get, oh God, that's -10, I must have screwed it up. Now, you're going to find that triple integrals can also be used to find things like volumes. And so if the context is you're finding a volume of something, in that case, shouldn't the triple integral be a number, right? Zeros and negatives don't make sense in that situation. So look at the context. If it's just an integral with no story beside it, all things are possible. If the story is the volume of something, or the surface area of something, or the mass of something, right? If it's got a story attached to it, then you know it must be positive, because those things exist in the real world, and they have to be positive.
I mean, I could imagine if it was something like you had say a circle or a sphere that was halfway submerged, and it said, find the percentage of the sphere that was above the water, and it was halfway submerged, you could have 0 because the top and the bottom would cancel each other out. But
yeah, but that, I guess if the context allows 0, I mean, you could have it. Can you imagine a sphere where on the surface of the sphere there was forces projecting outwards in the same direction as the point on the sphere to the origin? So it'd be like an explosion. If you were adding up all the directions, couldn't that be 0? Because of symmetry. So, I mean, yeah, in some contexts, 0 is possible. I don't know if you can get negative charges, but I guess if it's physically possible, it's doable. So let's do a triple integral with rectangular regions that is variable separable. And then we'll move on to, more and more complicated situations. So I want a triple integral that looks like this. It's going to be x equals 0 to x equals 1, z equals 0 to z equals 3, and y equals 1 to y equals 2. And it's e to the x, z squared, y. And we're doing it as dy, dz, dx. Are we comfortable about that question?
Would it be dx, dz, dy? Oh, dy, dz, dx. There we go. Never mind.
Right. Everything's matching, right? The y's are matching with these, the z's are matching. Now, in this case, do you see that the variables are separable? And since everything here is a number, because that has to be true as well, you can separate them. So I'm going to separate it as an x equals 0 to x equals 1 of e to the x times a z equals 0 to z equals 3 of a z squared times y equals 1 to y equals 2 of a y dy. Are you comfortable about you can separate them sometimes, but other times you can't? And when you do these guys, aren't you basically just doing Calc 2 stuff, right? Now, if you do this one, you're going to have e to the x evaluated at 0 and at 1. If you're doing this guy, you're doing 1/3 z cubed evaluated at 0 and at 3. And if you're doing this last one, you're doing 1/2 y squared evaluated at 1 and evaluated at 2. And this guy gets you e to the 1 take away 0. So e take away e to the 0 is 1. This guy gets you 9 take away 0. So this guy gets you 9. And this guy gets you 2 take away a half, which is 3 halves. So I guess the answer is 27 halves e minus 1. Hopefully I did that in my head right, but if it's not, tell me now. So right now, you shouldn't be scared of triple integrals. If it's a cuboidal region, and I'll probably end up calling it rectangular because it isn't, but if it's just numbers, isn't it pretty much plug and chug, right? There's no great algebra to worry about. Some can separate, and some can't. We good? Now, suppose you get a triple integral that looks like this. Z equals 1 to z equals 2. Y equals 0 to y equals 1. And x equals y to x equals z. Oh, z squared, take away 1. And the function we're going to integrate is just simply x. Are you comfortable about this triple integral? Have you noticed that what I've done is I've introduced a limit of integration? Have you noticed that in triple integrals, the limits could even have different variables in them? So this is a y in it, and this is a z. And the reason that's okay is because these two guys are coming later, won't they be able to compensate? You'll be able to introduce them. So if you take this guy first, you're now looking at z equals 1 to z equals 2, y equals 0 to y equals 1. And this guy is a half x squared, evaluated from x equals y to x equals z minus 1. So you integrate x with respect to x, you get a half x squared, put in these limits of integration. So z equals 1 to 2, y equals 0 to 1, and you're going to have 1 half z squared minus 1 squared, take away 1 half y squared. So far, so good. The next line is only to make integration easier. At least I think it's going to make it easier. I'm going to FOIL this out. So I'm going to get 1 half z to the 4, take away a z squared, plus a 1, take away a half y squared. Does it make sense why I did that line? Right. I don't really want to integrate that. I mean, you know, why make things hard when a little FOIL just makes it ugly, right? It's not difficult to do. If I left it that way, it'd probably be really, well, I'm not quite sure what I would do if I left it that way. Question, Terence.
Shouldn't foiling that out get you 2z squared?
Yeah, and then half, oh, yeah, but
Maybe
half
plus
of it
one
gets
half.
to 1. So the mistake, yeah, you got a mistake, but the mistake is it should be plus a half. Because it's z squared, which is z to the 4, take away 2z squareds plus 1, and then I took a half of everybody.
There was a mistake, but I identified the wrong one.
Yeah, but at least you knew it was a mistake, so we had to look at it and fix it. Now, in this one, we're going to integrate with respect to y. So this is going to be a half y z to the 4, take away y z squared, plus a half y, take away 1/6 y cubed, evaluated at y equals 0 to y equals 1, and then we'll do the dz. So it's now going to be, plug in 1. That's going to get 1 half z to the 4, take away a z squared, plus 1 half, take away 1/6, minus a whole load of zeros, so I don't care. That guy probably tied it up a little bit. 1 half z to the 4, take away z squared, that's a third. Okay, can I just dot that guy? Isn't that now calc 2? Now, I'm not going to do the next question. I just want to show you what it looks like. That is doable, isn't it? Z is going from this y value to that y value. Now, when we integrate this, can you imagine that you might have the z's will disappear, so you'll have just x's and y's jumbled up. When you do this, won't the y's disappear, but you'll have some function in x. And then when you do this, you're good to go. So there are some rules about what is possible. The first thing is the last integral. must contain numbers, right? So it must be x equals 1 to x equals 10. If that said x equals y to x equals 7, haven't you got your order of integration wrong? Because in the future, you're going to have to create the limits of integration x, y, and z. And if you think that the last one, this one here, I mean by the last one, has a variable in it, like x equals 3 to x equals y squared, you are wrong, right? Just say, okay, my order of integration is wrong. Maybe I should make that the second one, right? Not the last one, whatever. Okay. And each integral should reduce the variables by one term. What I mean by that is that if you integrate this with respect to z and you use these limits of integration, when you're finished, there won't be any more z's left, agreed? The z's will have turned into something with y's in it, right? And the y's that are there are still y's and the x's that are there, right? So when you're finished this integration here, shouldn't the answer be x's and y's in some kind? When you finish this second integration, shouldn't the answer only have x's in it? So why is that important? Can you imagine that this didn't say that it said this? Wouldn't that not be a valid integration? You see this z here? Shouldn't it have already disappeared? You can't have it reappear again, right? So
X.
you can have x's there, but you can't have an x plus z there, right?
Oh yeah, my bad.
Yeah, because if
I
you
thought, that,
integrate,
I thought that z was a 2.
oh, well, yeah. I put little strokes through my z's, but they still look like 2s if I'm not careful, right? Why am I saying that? Just so that when you are, if you're given the integral, it's fine, right? They're not going to screw up with the question, right? They're not going to give you, or they shouldn't at least, give you an integral that doesn't work. But if you're creating your own triple integral, aren't these kind of rules you have to be aware of what you can and cannot do? Now, for variables to be separable, the minute you introduce these things, isn't variable separable out the window? It's just not going to happen. Right, and you might get away with a minor x getting pulled out or something, but it's not really going to be your go-to technique. Are triple integrals kind of okay, although you haven't seen many of them?
Okay, I have a question.
Yes.
So say you had xy plus xz.
Okay, in some kind of triple integral, right?
Yes. Can I factor out the x?
Yeah.
And then can I do a double integral times a single integral?
Depends on the limits of integration.
Let's say they're all numerical.
Oh yeah. Well, actually,
Okay.
if these were all numerical, I would split this up, which is, I think, is what you're saying.
Yeah, that's exactly what I wanted to know, if that was legal.
Yes. As
Cool.
long as these are all numbers, you can do that. That might save you a little bit of work, right?
Yeah. It seemed too good to be true.
But it's true. As long as, we'll re-emphasize this,
All
as
of them are
long
numbers.
as these are numbers, you can get away with that. The minute they introduce an x or a y or in any of the limits of integration, you really can't separate them, because there's a variable there that if you separate it, will pop back in at the end when it should have disappeared on you, right? Because the whole trick is there shouldn't be any letters left when you're finished. And if there is a limit of, if there's a limit on the integration that has a variable, you're going to be in trouble. Okay, what you got? Right, I'm going to set up question 1. Won't do much except write it down, because I want you to get used to what it looks like in the textbook and in questions. Now, the only difference I would make, and again, this is a choice, See, I've already screwed up. That guy matches with him, right? So that means these are y's. The middle one is x's. So the center one is going to be x equals y to x equals 2y. And the inside one is z's. So this is going to be z equals 0 to z equals x add y. And then you're going to do an 18xy dz dx dy. So that might be what it looks like in WebDesign. For a lot of you, I hope it, I don't hope, but for a lot of you, this might be a much nicer way to write that question. It just doesn't make it easier to keep track of who each guy is and what the limits of integration are. But if you can handle this without needing to add this or rewrite it this way, that is totally fine. I'm just curious, because I am. See your last name, and while you're doing that, there's a little guy down here where you can wave at me. See him? That's under reactions. How many of you prefer to do the y equals 0, y equals 1 technique? In other words, the way I've done it. And be honest. How many? So 2 of you. Cool. Oh, now it's turned into Rose is sometimes yes and sometimes no. Right.
So I got a joke for you.
Oh, cool. Tell me.
So a frog goes to the bank and he wants to get a loan and he wants
Okay.
to go on vacation. So he goes up to the cashier. Her name is Patricia Wack. And he goes, I'd like to get a loan to go on vacation. I'd like $20,000. She goes, well, that's
Okay.
quite a large amount of money for a frog. We would really need to see some kind of collateral. And he goes, oh, no problem. And he pulls out a small figurine, made out of like porcelain. And she goes, well, I don't know about this. I'm gonna have to go talk to my boss. So she goes to her boss and she's like, well, this frog came in, he wants a loan. And I mean, and she holds up the figurine. She's like, what is this? And he goes, well, that's a knick-knack, paddywhack. Give the frog a loan.
Oh, God. Tessa, do you see what I have to suffer?
I kind of liked it.
I started it.
I did. I have no one to blame. That is my fault. Knick-knack, paddywhack,
Because her name
give
is
the
Patricia
frog a
Wack.
loan. Okay, I'll try and remember that. All right, Rosie, you get your hand up for a question now because we're finished for today now. I think that joke's a good place to stop.
Yeah, I have a question.
Mhm.
Can you enable the practice another on the homework for 5.5 point B and 5.6?